Welcome, curious minds, to the deep dive. Today, we're embarking on a journey into one of the most profound and, frankly, mind bending mysteries of our cosmos. Imagine, if you will, looking at this magnificent tapestry, right? Woven with incredible precision, stretching across billions of light years. But here's the truly astonishing part. What if most of the threads that hold it all together, the very fabric of reality itself, are completely invisible? What if our universe is overwhelmingly dominated by something we just can't touch, see, or directly detect with, well, any of our current instruments? For decades, scientists have grappled with this enigma, something that fundamentally challenges our understanding of what matter even is. Dark matter. It sounds like something straight out of science fiction, doesn't it? Kind of like a phantom ingredient in the cosmic recipe, elusive and, well, ethereal. But as we'll unpack today, it's not only one of the most rigorously tested and widely accepted concepts in modern astrophysics, its existence isn't just hinted at by observations, it's actually demanded by both the grand scale of the universe and, get this, the fundamental theories of particle physics itself.
Indeed. And today we're embarking on a deep dive into the overwhelming and diverse lines of evidence for dark matter. It's quite a story. We'll explore not only how scientists first figured out it had to exist through these strange cosmic behaviors, but also, critically, how its absence in certain places that paradoxically solidifies its reality, which is fascinating. And what's truly fascinating, I think, is that from a purely theoretical standpoint, even without the astronomical observations, new fundamental particles and forces seem to be an inescapable conclusion for physics itself. It's like physics is telling us there's more out there. So this deep dive will offer you a shortcut, hopefully, to understanding why dark matter is considered so real, what it tells us about the structure and evolution of our universe, and the fundamental particles that might actually make it up. It really challenges us to ask, is the real question, does dark matter exist? Or maybe, are new particles and forces required to explain our universe? And the answer from all major theoretical frameworks in both astrophysics and particle physics seems to be a resounding and unequivocal yes.
Get ready for some serious aha moments because we've gathered some truly fascinating insights. We're pulling from cutting edge research and the perspectives of leading scientists who've really been at the forefront of this discovery. Okay, so let's cast our minds back. Way back to the dawn of this mystery, to the first kind of subtle whispers from the cosmos that something invisible was at play. Imagine peering through a powerful telescope at a distant galaxy, right? And instead of seeing everything moving predictably, you observe something truly bizarre. You see these vast streams of material, seemingly ordinary hydrogen gas, stretching out and away from the main galactic body. It's like, I don't know, like an invisible colossal hand is pulling at it with immense force. That's precisely what astronomers observed with a galaxy called UGC 10214. It was an early, really tantalizing hint at a gravitational influence way beyond what its visible matter could possibly account for.
Exactly. And that wasn't just a one-off, an isolated anomaly. Similar strange behavior started popping up in the astronomical record. Take the remarkable discovery in the year 2000 by Robert Minchin and his team at Cardiff University, a really key moment. They were meticulously surveying the Virgo cluster of galaxies with a radio telescope perfect for detecting that cold hydrogen gas. And amidst the expected galactic structures, they spotted two apparently isolated clouds of hydrogen. Strange. One of these clouds, well, it had a faint visible galaxy associated with it, like you'd expect a clear partner. Okay, fine. But the second one, which they named Virgo H121, was truly baffling. It had no visible galaxy whatsoever, none. Just this cloud hanging out there. Yet its motion was unmistakable. It was moving with a velocity that could only be sustained if it were gravitationally bound to something incredibly massive. Minchin concluded that this solitary cloud had to be just a small, visible tracer of a much larger, completely unseen object. Something as massive as 100 billion suns. That's huge. This wasn't just some vague hint. It was direct, pretty undeniable evidence pointing towards these invisible, massive structures shaping the universe. It was kind of like finding a feather floating in midair and realizing there has to be an invisible bird holding it up, right?
That's a fantastic analogy. Yeah, the invisible bird. And it brings us directly to our next powerful piece of evidence, where none other than Albert Einstein himself makes an appearance. You might know that incredibly massive objects in space don't just pull on other matter, they actually bend the fabric of space-time itself, warp it. This bending, in turn, diverts the path of light. Much like a magnifying glass or maybe a warped pane of glass can distort what you see through it. This phenomenon, known as gravitational lensing, was predicted by Einstein's general theory of relativity, and it's since become one of our most potent tools. Really powerful. It basically acts as a universe-sized telescope, letting us see gravity's footprint, even if the source of that gravity is entirely invisible to our normal telescopes.
Precisely. And the key here is that the amount of distortion we observe, how much the light is bent, it directly tells us the strength of the gravitational field, and therefore it tells us the amount of mass responsible for it. So this method can be used essentially as a gravitational telescope to find invisible or dark matter. You're weighing the universe by how it bends light. Consider the galaxy cluster Abell 2218, this huge cosmic metropolis. Deep optical images reveal distant background galaxies stretched and distorted into these incredible elongated arcs and rings, almost like smeared paint across the sky. The truly perplexing part, when astronomers carefully added up all the light from the visible galaxies and the hot gas in the foreground, there just wasn't enough visible mass there. Not nearly enough. Not enough to account for such significant gravitational distortion. The math didn't add up. The researchers, in a paper titled "Where is the Matter in the Merging Cluster Abell 2218?" they actually articulated their astonishment. They basically said, where is it? They confirmed they found evidence for two structures corresponding to two large-scale dark matter clumps. Huge clumps of invisible stuff. This wasn't just theory. It was a concrete demonstration that gravitational lensing could not only locate, but also map and study invisible matter in the universe. It's like seeing the footprint without seeing the giant. And it's really crucial to understand that this isn't some atmospheric trick, some optical illusion from Earth's own air messing things up. Gravitational lensing is achromatic. That means it doesn't split light into different colors based on wavelength, unlike a prism or, say, atmospheric refraction. Atmospheric effects, when light passes through varying densities of air, they are chromatic. They cause slight color separation, like tiny rainbows sometimes. Scientists rigorously check for and eliminate any chromaticity in their observations. They have to be sure. This meticulous process leaves no doubt that these distortions are caused by immense mass, regardless of whether that mass emits light or not. It's the gravity itself that's doing the talking.
That's a really powerful distinction. Okay, so we've seen how invisible mass can make itself known through these ghostly tugs and by bending light. But let's bring it closer to home, to the grand cosmic merry-go-round of galaxies themselves. In our own solar system, everything makes intuitive sense, right? Planets closer to the sun orbit faster, Mercury zips around, Neptune crawls along, while those farther away move slower. It's all perfectly governed by Newton's laws of gravity. Seems straightforward. You'd absolutely expect the same dynamic for stars in a spiral galaxy. Stars closer to the galactic center, where most of the visible mass, the stars and gas, is concentrated. They should zip around quickly, while those way out in the outer arms should just drift along at a much more leisurely pace. That's the classical expectation. That's what Newton would predict.
And that's precisely not what we observed. Not even close. The first hints of this cosmic anomaly actually emerged way back in the late 1920s. A Dutch astronomer named Jan Oort was making measurements of stellar motions in our own Milky Way galaxy. He found that stars far from the galactic center maintained almost constant speeds, rather than slowing down as expected. It was puzzling, but maybe not conclusive enough at the time to really overturn established physics. The data wasn't perfect. Then, in 1933, the rather eccentric Swiss astronomer Fritz Zwicky, brilliant guy, but apparently quite a character, was observing the Coma galaxy cluster. He noticed something similar. Galaxies within the cluster were moving at speeds far too high to be held together by the visible matter alone. They should have flown apart. He actually coined the term dark matter, Dunkel Mattercurie in German right then, speculating about some unseen mass providing the additional gravity needed. But, partly due to his, let's say, abrasive personality and partly due to the limited quality of the data available back then, his revolutionary ideas weren't widely accepted. People kind of shrugged it off.
Right, so Zwicky, despite his pioneering insight, wasn't really taken seriously then, which is a shame in retrospect. But the universe doesn't care about personalities, does it? That fundamental anomaly, that weirdness, was still there, just waiting to be rediscovered with more rigorous methods. And that's precisely what Vera Rubin and W.K. Ford did decades later, a landmark moment in astrophysics. In 1970, working independently of Zwicky's earlier, kind of forgotten work, they definitively found the same anomaly again. No question this time. First, they looked at the neighboring Andromeda Nebula, our big galactic neighbor. And then, through meticulous studies of 60 other spiral galaxies, they kept seeing the same pattern. Over and over. What they consistently found was that stars in the outer regions of these galaxies were moving far too fast, way too fast to remain gravitationally bound by the visible matter alone. They should have simply flown off into intergalactic space, gone rogue, but they weren't. They were sticking around. So, plotting stellar velocity against the distance from the galactic center, what we call the rotation curve, instead of seeing the expected decrease in speed, like a hill sloping down, they observed an almost flat line. Flat. extending far beyond where the visible matter, the stars and gas, trailed off into darkness. This implied that the galaxy's total mass must increase proportionately with its radius, extending far out into what appeared to be empty space. It was a clear, undeniable signal that a huge, invisible halo of matter was contributing most of the gravitational pull, keeping those fast-moving outer stars from escaping. Like an invisible anchor. That's a truly foundational discovery.
Yeah, reshaping our entire picture of what a galaxy is. Mostly invisible stuff, apparently. Now let's zoom out, way out. From individual galaxies to the universe as a whole, to a phenomenon that lets us literally look back in time. Imagine looking at the universe when it was just a baby, a mere 375,000 years old. That's incredibly young in cosmic terms. Long before the first stars or galaxies even dreamed of forming. That's what the cosmic microwave background, or CMB, allows us to do.
It's this omnipresent, almost perfectly uniform, faint glow of electromagnetic radiation. It's in the microwave region of the radio spectrum, and it's essentially the leftover light, the afterglow from the Big Bang itself. It's like the universe's first photograph, right? A relic from an era when the universe finally cooled enough for light to travel freely without constantly bumping into things.
Indeed, the CMB is, well, people call it the universe's DNA. It provides absolutely crucial clues about its early structure and its fundamental composition, what it's made of. By precisely measuring the subtle temperature fluctuations, these tiny hot and cold spots, just fractions of a degree difference in this ancient light, and then analyzing the patterns and peaks in its power spectrum, how those fluctuations vary at different angular scales on the sky. We can reconstruct the conditions of the early universe with incredible accuracy. It's like decoding a cosmic blueprint. These peaks are exquisitely sensitive to the universe's ingredients. The density of ordinary matter, the stuff we're made of, the density of dark matter, the density of dark energy, even the overall geometry of space itself. And here's the key insight for you. When cosmologists create these incredibly sophisticated computer simulations of the early universe and its evolution, and they include dark matter in their models, in the precise amount suggested by galactic rotation curves and gravitational lensing, about 5 times more than ordinary matter. These simulations produce a CMB power spectra that fits the actual observations from satellites like WAP and Planck like a glove. It's a perfect match. Whereas models without dark matter, they simply fail. Miserably. They drastically fail to reproduce the observed patterns in the CMB. So this isn't just a hypothesis that dark matter might be there. It's a critical, indispensable component for our best and most accurate models of the universe's birth and early development. The CMB data offers an independent, consistent, and exceptionally strong validation for dark matter's presence. It's baked into the very fabric of the early cosmos.
Okay, so if we just step back for a moment and take all that in, everything we've just discussed, what's the truly mind-blowing takeaway here? It's not just that we have one or two hints, or even a few disparate observations pointing to something missing. That would be interesting, sure. But what's truly remarkable, what makes the dark matter hypothesis so incredibly robust and compelling, is that all these different lines of evidence converge on the same conclusion. They all point the same way. The missing matter, calculated from light bending around invisible objects in galaxy clusters, right? That lensing effect. The anomalous, flat rotation curves of stars and spiral galaxies discovered by Rubin and Ford, and even the subtle patterns, the peaks and valleys in the universe's ancient baby picture, the cosmic microwave background. 3 entirely different methods, looking at vastly different scales of the cosmos, from the local galactic neighborhood to the entire observable universe just after the Big Bang. All deliver the exact same consistent answer about how much dark matter there must be. About 85% of all matter, roughly.
That convergence, that unanimous vote from the universe itself, is arguably the most powerful insight into its reality.
Yeah.
It's just overwhelming. This isn't merely an isolated piece of evidence you could maybe explain away somehow. It's a symphony of observations, each independent, using different physics, different techniques, looking at different eras, yet all singing the same tune, all pointing to a universe that is far more mysterious and filled with unseen matter than we could ever imagine based on just what we can see. Each piece of evidence strengthens the others, building an almost irrefutable case. It's hard to argue against that level of consistency. It's truly a testament to the scientific method, I think, and our ability to deduce the invisible from its profound gravitational influence. We can't see it, but we can feel its pull everywhere.
That symphony of evidence is truly compelling. Yeah, it's hard to ignore when everything lines up like that. So if it's there, this invisible scaffolding, this dark matter, what exactly is it doing for the universe on the grandest scales? And how else can we catch glimpses of it? The Big Bang, as we know, was this incredibly energetic, chaotic event, matter flying outwards at immense speeds. The early universe was hot and dense, but also remarkably smooth, almost uniform, according to the CMB. So it's actually difficult to explain how, from such a uniformly energetic and rapidly expanding state, these colossal structures like galaxies and vast cosmic filaments could have formed. How did they clump together? It seems like everything should have just kept expanding, getting more diffuse. It's like trying to build an intricate sandcastle as massive waves are constantly washing in. There must have been some cosmic glue holding things together early on.
And that cosmic glue, that indispensable architectural element, is dark matter. That's the leading theory, and it works beautifully. The observed large-scale structure of the universe, this cosmic web, these filaments of galaxies and clusters surrounding vast empty voids, it requires the existence of dark matter. Without dark matter's immense gravitational pull acting as a stable cosmic scaffold, ordinary matter, stuff that interacts with light, would have been pushed around too much by radiation pressure in the early universe. It just couldn't have clumped together quickly enough. Ordinary matter couldn't have collapsed against the outward push of expansion and radiation to form the intricate galaxies and galaxy clusters we see today in the time available. So while ordinary matter eventually collapses into stars and stellar systems on smaller scales, dark matter provides the overarching gravitational framework upon which everything else is built, like an invisible skeleton for the cosmos. It essentially provided the initial gravitational seeds, these slight overdensities, that ordinary matter could then fall into and accumulate around, eventually forming galaxies. Now, what's fascinating here is that the universe isn't static. It's a dynamic, often violent place. Collisions between galaxies or entire galaxy clusters, mergers where galaxies combine, intense tidal forces from massive objects ripping smaller ones apart, even powerful explosions like supernovae. These intense interactions can actually separate dark and ordinary matter because they interact differently. Dark matter mostly just feels gravity, while ordinary matter also feels friction, pressure, electromagnetic forces. So when dark matter gets stripped away from ordinary matter due to these cosmic motions, it can leave behind visible galaxies without their dark matter halos. Or conversely, you could end up with dark matter clumps floating around with hardly any ordinary light-emitting matter attached. These scenarios where dark matter's presence, or crucially its absence, is dramatically highlighted, offer some of the most profound and frankly counterintuitive proofs of its existence. This is where the story gets really interesting, because sometimes the most compelling evidence comes from what isn't there.
That's truly incredible to think about these violent cosmic interactions literally pulling the visible and invisible stuff apart. Wow. So it begs the question, could these separations be so extreme that we end up with, say, an entire galaxy that's almost completely invisible, made up predominantly of dark matter with hardly any stars? And what would that even look like? Or maybe not look like? These dark galaxies aren't just theoretical ideas, are they? You mentioned they've actually been detected, often through that gravitational lensing trick.
Absolutely. And we have concrete examples right here in our cosmic neighborhood that fit this description perfectly. They really bring home the concept of dark matter's dominance. Take the Milky Way's dwarf satellite galaxies, Segue 1 and Segue 3. These are tiny, incredibly faint galaxies orbiting our own. You can barely see them. They contain only a few hundred ordinary stars. Just a handful, really. Yet based on the computed velocities of those few stars, how fast they're moving their gravitational pull suggests they harbor a mass equivalent to 600,000 suns. That's a lot of mass for so few stars. This leads to an absolutely astounding dark-to-ordinary matter ratio of something like 1,000 to 1. Compare that to the typical 5 to 1 ratio we see in most large-scale structures, like bigger galaxies. So Segue 1 and 3 are essentially dark galaxies. They possess immense mass, but emit almost no visible light. They're mostly invisible gravitational blobs with a few stars sprinkled in.
And this phenomenon, finding these dim, mass-heavy dwarfs, it directly addresses a fascinating puzzle astronomers faced for years, didn't it? The missing satellites problem. I remember reading about that. Early computer simulations of the universe's evolution, like those from people like Ma-Chung Pei at UC Berkeley, Edmund Bertschinger at MIT, and groups led by Anatoly Klipin and Ben Moore, they consistently predicted thousands, literally thousands, of small dark matter halos, potential sites for dwarf galaxies orbiting around larger galaxies like our Milky Way. But when astronomers actually looked through their powerful telescopes, they only observed about 60 visible ones, way fewer. This is a major nagging discrepancy. It made people wonder if the whole cosmological model was wrong.
Exactly. And this discrepancy initially led some to seriously question the underlying cosmological models, the lambda CDM model that includes dark matter. However, as Charles Keaton, an astrophysicist at Rutgers University, perfectly summarized the resolution, we were comparing apples with crab apples. A great way to put it. The simulations were predicting dark matter subhalos, these concentrations of dark matter, just the invisible stuff. While the observations were focused on visible dwarf galaxies, the ones that actually managed to form enough stars for us to see them easily, The key insight, the resolution, is that not every dark matter halo necessarily hosts a visible galaxy. Just because the dark matter clumped doesn't mean stars automatically form there. There are many astrophysical mechanisms, especially these low-mass subhalos, that could prevent stars from forming efficiently. Maybe the gas needed to form stars was too sparse, or it got blown out early on, or it was stripped away by the gravitational pull of the larger host galaxy. This could leave many of these dark matter halos essentially empty of stars, leaving them, as Keaton puts it, lurking beyond our vision, never to be seen directly. Dark and empty scaffolds.
But we can see them indirectly, right, just not with visible light, using gravity again. Researchers like Neil Dalal and Chris Koshenek, understanding this potential mismatch, they used sophisticated gravitational lensing analysis. They looked at how the light from distant quasars was subtly distorted. They figured out how much dark matter substructure, how many of these smaller clumps, was needed around foreground galaxies to explain those specific lensing anomalies they were observing, and their findings. They were perfectly consistent with the computer simulations that had predicted many more satellite galaxies than were seen visibly. It strongly hinted that the missing satellites weren't really missing at all. They were, in fact, these dark dwarf galaxies, too dim to be directly observed, but massive enough to affect light gravitationally.
And the evidence just keeps piling up. It's really exploded in recent years. In June 2015, Jin Koda's team at Stony Brook University, by meticulously examining archival images from deep surveys, found 47 of these ultra-diffuse, likely dark matter-dominated galaxies in the Coma cluster. Expanding their search, they then discovered another 854 potential dark galaxies, with 332 of them appearing as large and angular size as our own Milky Way, just incredibly faint. Further calculations led the team to conclude that the Coma cluster could harbor over 1,000 dark galaxies, effectively matching its count of visible galaxies. Mind-blowing. Half the galaxies might be nearly invisible. And Coma isn't unique. In August 2015, Christopher Mijos and his colleagues reported finding 3 more in the relatively nearby sparsely populated Virgo cluster. Then in 2016, Vanderberg and collaborators found nearly 800 more of these ultra-diffuse dark galaxies hiding in 8 other galaxy clusters. They seem to be everywhere once you know how to look. As astrophysicist Michael Beasley notes, we don't know how many there are, but we know there are a lot of them. It's a huge population we were mostly blind to. He even theorizes they could eventually outnumber the estimated 2 trillion bright galaxies in the observable universe. Imagine that, more dark galaxies than bright ones. Our cosmic senses is being radically rewritten.
That's a truly astonishing thought. A universe potentially teeming with invisible galaxies. Wow. But here's where it gets really interesting. Maybe the most counterintuitive part of the whole story. A truly paradoxical and utterly compelling piece of evidence. If dark matter is so absolutely essential, right, for holding galaxies together, for providing the gravitational scaffold for their formation, as we've established, what happens when a visible galaxy, against all expectations, loses it? Or maybe never had much to begin with? The absence of dark matter in certain galaxies, rather than undermining the whole hypothesis, actually provides compelling, almost irrefutable proof of its existence and necessity elsewhere. Think about it. We're saying dark matter is essential to hold galaxies together and explain their motion. So what's the most surprising yet convincing way to prove that? By finding a galaxy where it's missing and then observing precisely the kind of gravitational weakness and instability you'd predict without it. It's like proving the crucial need for, say, scaffolding by showing a building that's unstable or even collapsing where the scaffolding was never put up or got removed. The absence demonstrates the necessity. It's proof by absence.
Exactly. This proof by absence is incredibly powerful. It flips the script. In 2018, Peter Van Dockum and Shani Danieli made a groundbreaking discovery that really shook things up. They found this very diffuse, ghostly-looking satellite galaxy, designated DF2, orbiting the big elliptical galaxy NGC Unit 1032, and the kicker. This galaxy had almost no dark matter, maybe none at all. Its mass was essentially accounted for just by its stars. That's highly unusual. How did they know? Well, the stars and the globular clusters within DF2 were moving incredibly slowly, orbiting at a mere 8 kilometers per second. That's glacial for a galaxy. If dark matter were present in the typical proportions, which is about that 5-to-1 ratio compared to ordinary matter, their speed should have been much higher, closer to 30 kilometers per second. DF2 is not unique either. Since then, a small but growing population of these ordinary matter-dominated dark matter-deficient galaxies has been recently found, all showing a similar telltale slowness in their internal motions. So, okay, how do these galaxies lose their crucial dark matter halos? Or maybe they never formed them properly. Well, these dark matter-free galaxies are almost always found very close to much more massive galaxies. That seems to be the key clue. DF2, for instance, is orbiting near the massive galaxy NGC 1052. The immense gravitational pull from these massive neighbors causes powerful tidal forces. Think of how the moon pulls on Earth's oceans to create tides. On a galactic scale, these tidal forces can be strong enough to preferentially strip away the more loosely bound dark matter halo from the smaller galaxy, while leaving the more tightly bound stars relatively intact, at least initially. It's like gravitationally sifting the dark matter away. And we even see evidence of this happening. A narrow tidal stream of matter has been observed being pulled off another such galaxy, DF4, which is close to NGC 1035. This strongly suggests a recent violent separation event where its dark matter was gravitationally ripped away by its massive neighbor.
And the consequence of this catastrophic loss, this gravitational stripping, is exactly what we would predict if dark matter is real and necessary, right? It further solidifies the case. Once stripped of their vital dark matter component, these galaxies are gravitationally weakened. They're unstable. They become unable to form new stars over long periods because they lack the necessary deep gravitational well to pull in and condense the required gas. Star formation just fizzles out. And over time, they become more diffuse, puffier, with the remaining stars moving ever more slowly in these wobbly, unstable orbits, which is precisely what we observe in DF2 and these other similar galaxies. This directly confirms that dark matter is absolutely required to hold ordinary matter together in gravitationally bound structures like galaxies over cosmic time. Without it, these galaxies would simply disintegrate, ripped apart by tidal forces from neighbors or even just internal dynamics within maybe a few 100 million years. A relatively short time, cosmically speaking. This proof by absence is such a stark reminder of dark matter's fundamental structural role in the universe. Its absence speaks volumes. That's incredibly clear, yeah. The absence truly proving the rule. Powerful stuff. Now, let's talk about arguably the most dramatic, the most visually stunning illustration of dark matter's separate existence. The bullet cluster. This isn't just an observation. It's a spectacular result of two colossal galaxy clusters that have smashed into each other at immense speeds, about 3.8 billion light years away. And it's given us what many, many scientists call the absolute smoking gun for dark matter. It's hard to argue with this one. It's like a cosmic car crash playing out on an unimaginable scale.
It truly is spectacular. When we observe the bullet cluster, we combine data from different kinds of telescopes, looking at different wavelengths, to get the full picture. In the composite images you often see, X-ray data from the Chandra satellite reveals the hot glowing gas. This shows up as two distinct pink clumps in the common visualizations. This hot gas, which emits X-rays, contains most of the ordinary visible matter, the baryons in the two original colliding clusters. So pink is where the normal stuff mostly is. However, when we perform gravitational lensing analysis on the same region, remembering how light bends around mass, regardless of whether it's visible or not, we find where most of the total mass is actually located. And this is typically indicated by the blue areas in those images. And here's the crucial part, the smoking gun. During this incredibly high-speed collision, the hot gas from each cluster, being made of ordinary matter, slammed into each other. It interacted electromagnetically, creating shock waves, and was significantly slowed down by drag forces, kind of like air resistance. That's why it's glowing in X-rays and lagging behind. But the dark matter clumps shown in blue, which interact very weakly with themselves or with the gas, except their gravity, they just sailed right through each other, almost unimpeded. So the dark matter clumps, blue, moved ahead of the hot gas clouds, pink. They separated. This stunning physical separation where the gravitational mass, blue, moved distinctly ahead of the ordinary baryonic matter, pink, provides incredibly direct, almost irrefutable proof that dark matter is a distinct, non-ordinary form of matter. This observation directly rules out many alternative theories that propose only modified gravitational laws without invoking new particles or forces. Why? Because you simply wouldn't get this physical separation of the center of mass from the center of the visible matter if gravity were just behaving differently. It was just modified gravity, the gas and the inferred mass should have stayed together, right? The bullet cluster is a profound demonstration that dark matter is a real, separate substance, interacting primarily through gravity and making up the vast majority of the universe's mass. It's like a truly spectacular cosmic experiment playing out right before our eyes, separating the components for us to see. Hard to misinterpret that picture.
That's a truly powerful visual confirmation. Yeah, the bullet cluster is just iconic. Okay, so here's where we pivot a bit. We shift from the observational bedrock of astrophysics to the cutting edge of fundamental theory, particle physics. Because even if we didn't have all these incredible astrophysical observations, the weird galaxy rotations, the lensing, the CMB, the bullet cluster, the fundamental theories of particle physics themselves strongly suggest that our current understanding of elementary particles is incomplete. Seriously incomplete. The standard model of particle physics, I mean, it's been incredibly successful, right? Describing the basic building blocks and forces we know. But it isn't a complete theory. It has these glaring gaps, inconsistencies, missing pieces in the grand cosmic puzzle. It feels unfinished.
That's absolutely right. Our most fundamental theories, while stunningly successful in their domain, reveal these subtle imbalances or problems. Things that shouldn't work the way they do, theoretically. We talk about broken symmetries or hierarchy problems. For instance, the Higgs boson, finally discovered in 2012 after decades of searching, a huge triumph. Well, it was found to be much, much lighter than expected, based on quantum corrections within the standard model itself. Its mass should have been enormous, theoretically, unless something else is going on. This fine-tuning problem is a major theoretical headache. Why is the Higgs so light? Some leading theories propose new particles, for example, hypothetical supersymmetric partners for every known particle, precisely to stabilize the Higgs mass naturally. Without these new particles, the standard model runs into theoretical difficulties, suggesting it's really only part of a larger, more complete picture. Physics is telling us there must be more.
And this isn't unprecedented in the history of science, is it? Sometimes theory actually leads the way, predicting particles that are only discovered later. Think about Albert Einstein and William de Sitter. Way back in 1932, they theoretically predicted large amounts of undetected matter based purely on applying general relativity to an expanding universe. Ironically, that was a year before Fritz Zwicky proposed dark matter based on its cluster observations, though the connection wasn't really made explicit back then. Theory hinted at it first. And another really famous example is Paul Dirac. Based purely on the mathematical symmetry in his equations describing electrons, he predicted the existence of antimatter particles, positrons. And just a few years later, the positron, the antiparticle of the electron, was discovered experimentally. Mathematical elegance, it seems, often hints at deeper physical reality.
Exactly. And today, the theoretical imperative for new particles is arguably even more robust, coming from multiple directions. Dark matter isn't just some ad hoc fix invented solely for astronomical problems. It's actually predicted by some of our most sophisticated mathematical theories trying to unify physics, like superstring theory. Many versions of string theory are based on something called supersymmetry physics. Supersymmetry postulates this deep fundamental symmetry between matter particles, like electrons and quarks, which are fermions, and force-carrying particles, like photons, which are bosons. If supersymmetry is real, it requires additional superpartner particles for every known particle in the standard model. Many of these hypothetical superpartners have exactly the right properties. Massive, weakly interacting to be dark matter. Garrett-Lisi's E8.E8 superstring theory model, for example, explicitly requires the existence of currently undiscovered matter particles to complete its mathematically elegant ensemble of predicted particles. So these advanced theories aren't just compatible with dark matter, they often needed to be mathematically consistent and complete. It falls out naturally from the equations.
Wow. And there's another fascinating theoretical angle too, right? Related to symmetry, but a different kind. Parity symmetry. This is about the left-handedness or right-handedness of particles, kind of like our hands being mirror images but not identical. If you imagine an event and its mirror image, parity symmetry basically dictates that the laws of physics should be exactly the same for both, like looking in a mirror shouldn't change the fundamental rules. But in our universe, we've observed certain fundamental interactions, specifically the weak nuclear force, that actually violate this mirror symmetry. They show a preference for left-handed over right-handed particles. It's weird. This observed asymmetry suggests a potential imbalance in the universe. And one elegant theoretical solution is that maybe there's a corresponding mirror universe or a hidden mirror sector where the opposite preferences apply, perfectly balancing the cosmic ledger. And the particles in that mirror sector, they could very well be the dark matter particles we're looking for, interacting with us primarily through gravity. Similarly, the fact that we haven't discovered vast amounts of antimatter particles at cosmic scales, despite the Big Bang theoretically producing equal amounts of matter and antimatter, well, maybe that missing antimatter is lurking in some hidden universe or sector needed to restore charge parity symmetry. The universe, in its quest for balance and symmetry, seems to demand more constituents than what we currently see in the standard model.
What's also just striking is the sheer scale of the unknown that our current physics hints at. The energy scales we haven't explored. Our current experimental discoveries in particle physics, from the largest cosmic scales down to the smallest things probed by accelerators like the LHC, span about 45 orders of magnitude in size. That's an enormous range we've explored. However, the theoretical limit, the fundamental scale where quantum mechanics and gravity must meet the Planck length, is a staggering 16 orders of magnitude smaller than what we can currently probe experimentally. To put those numbers into perspective, the difference between the size of a galaxy and a human is roughly 20 orders of magnitude. We're talking about a gap in our knowledge far, far larger than that. It's an incredibly small scale where space and time itself might behave in ways we can barely conceive, a vast, unexplored quantum frontier, where entirely new particles and forces could easily be lurking, completely unnoticed by our current tools, simply because we haven't yet built experiments sensitive or energetic enough to find them. It strongly suggests the standard model is just the tip of the iceberg. So here's the really key takeaway for you listening. Many different theoretical models, often developed completely independently of any astrophysical observations, necessitate new particles. They need them to resolve internal inconsistencies, to restore broken symmetries, or to complete their mathematical structure. When these purely theoretical requirements line up so perfectly with the completely independent astronomical observations demanding dark matter, it creates an incredibly powerful convergent argument. It almost doesn't matter if we end up calling these new particles dark matter particles or something else. The fundamental point is that new types of matter, new particles, new forces perhaps, are required to explain both the universe we observe and to complete our fundamental theories of physics. This means that even if we redefine exactly what dark matter is in the future, the underlying need for physics beyond the standard model persists. In fact, it grows stronger with every new piece of data and theoretical insight. Hashtag 3.2, alternative theories and the core question.
That's a really profound statement. New particles seem required regardless of whether we specifically call them dark matter. That's a deeper need. But what about those alternative ideas we sometimes hear about? The ones that try to explain these cosmic puzzles, like the weird galaxy rotations, by modifying our understanding of gravity itself rather than adding new matter. Theories like modified Newtonian dynamics, or MOND, for example. They attempt to explain some of these galactic rotation anomalies without explicitly invoking dark matter particles. They propose a different solution to the gravitational discrepancies, changing the rules of gravity instead.
Right. And MOND is a prominent example. These alternative hypotheses, like MOND, are actively explored by some researchers, and it's important science. They've had some intriguing success in explaining specific galactic rotation curves, particularly in spiral galaxies, without needing dark matter within the galaxy itself. However, it's crucial to note that even these alternative gravity theories often run into trouble explaining the full range of observations. And critically, they often still end up requiring new particles and forces themselves to be fully consistent or to address all the phenomena that dark matter explains so well. The source material highlights this clearly. Even alternative theories of gravity, like MOND, often necessitate additional elementary particles to work on larger scales or fit with cosmology. For instance, while MOND aims to tweak Newton's laws at very low accelerations, like those found at the outskirts of galaxies, making it fully compatible with observations like gravitational lensing in galaxy clusters, the dynamics of things like the bullet cluster, and especially the precise details of the cosmic microwave background. Well, that usually requires introducing something new. Often, MOND needs to be extended to include a new field or particle, perhaps a sterile neutrino, a hypothetical type of neutrino that interacts even more weakly than normal ones, or other exotic particle fields. By some estimates, these MOND-compatible particles, needed to make the theory work cosmologically, would still account for almost two-thirds of the mass equivalent of ordinary matter in the universe. So in effect, even MOND ends up needing its own form of dark matter, albeit one perhaps tied more directly to a modified gravitational theory, rather than being a completely separate substance like standard WIMPs. It doesn't completely eliminate the need for new, unseen stuff. Which brings us back to that more fundamental question we raised earlier. Maybe the central question isn't just, does dark matter, as traditionally conceived, exist? But rather, are new particles and forces fundamentally required to explain our universe? And the overwhelming answer to that question, coming from basically all major theoretical frameworks, whether it's standard cosmology with dark matter, string theory, supersymmetry, or even attempts at modified gravity like MOND, the answer is a resounding yes. This really moves the discussion beyond a simple dark matter versus modified gravity debate. It points to a deeper, more profound realization. Our current particle physics model, the standard model, is by all accounts incomplete. It's missing crucial pieces. The core necessity remains, whichever path you favor. We need something new, something beyond our current understanding to make sense of the cosmos. Physics itself is telling us there's more to discover. Hashtag 3.33. The multiverse connection. Speculative, but rooted in theory.
Okay, so we're talking about a universe that seems to be fundamentally demanding new particles, new physics. Could dark matter, Could it even hint at something as wild as mind-bending as the multiverse? The idea that our universe isn't the only one. I know it sounds like sci-fi, but several theoretical models, even within standard cosmology and mainstream particle physics, actually seem to require or at least naturally predict a multiverse to resolve various puzzles. Things like the fine-tuning problem, why the constants of nature seem so perfectly set for life, or ideas emerging from eternal inflation theory, which suggests our universe might just be one bubble in an ever-expanding cosmic foam of universes.
Indeed. And it's a fascinating, though admittedly speculative, connection. The idea gaining traction is that dark matter might not just be one single type of particle. Instead, it could be a whole collection of particles, maybe even a whole complex sector of reality that inhabits what physicists are now theorizing as dark sectors. You can sort of imagine these dark sectors as being like parallel universes, or maybe hidden dimensions, each potentially with its own unique fundamental forces and particles, largely separate from our ordinary matter universe, the one described by the Standard Model. In some scenarios, these dark sectors might be so fundamentally separate that they don't share any common particles or forces with our universe, except for gravity. Gravity might be the only bridge. In that case, there'd be absolutely no way for us to causally interact with them or them with us beyond feeling their overarching gravitational pull. It's like having multiple complex ecosystems on Earth that only share the planet's gravity, but are otherwise completely isolated. However, and this is where it gets potentially observable, if some particles within these dark sectors, hypothetical particles like dark photons or axions, can mediate between sectors, if they can interact, even very, very weakly, with ordinary matter, then subtle causal connections could exist. We might be able to detect faint signals from these dark sectors through these portal particles. This suggests potentially a whole spectrum of universes or sectors, some with relatively stronger, albeit still incredibly faint, interactions with our own through these mediating particles, and others perhaps with no common forces or particles at all, where maybe only the additional gravity generated by their dark matter might be detectable by us, perhaps through subtle gravitational lensing effects on cosmic scales. This really expands our potential understanding of dark matter way beyond just being some missing mass in our own local cosmos. It hints at a much richer, more complex reality, where our universe might just be one layer, one sector among many. The very nature of dark matter, its properties, its potential complexity, could be a window, our first real observational hint into these other unseen realms. It suggests the universe is not just bigger than we think, but possibly more diverse in its fundamental makeup than we ever imagined. It's a truly humbling thought, pushing the boundaries of science. Hashtag 4.1. Why the dark matter hypothesis prevails. Hashtag 4.1. Unparalleled explanatory power.
That is truly mind-bending. Yeah, the idea that dark matter could be our first tangible hint of a wider multiverse. Incredible. But let's bring it back, just for a moment, to the here and now, to the working consensus in cosmology and astrophysics. Given all this overwhelming evidence we've discussed and the theoretical necessity we just explored, why does the dark matter hypothesis, the idea of actual new particles making up most of the universe's matter, remain the most widely accepted theory among scientists? It seems pretty simple when you lay it all out, doesn't it? There just isn't any single alternative theory that can adequately explain all the different observations across all scales to the extent that the standard dark matter hypothesis does.
That really is the core of it. It comes down to what we call convergent, consistent, comprehensive evidence, the sheer explanatory power across diverse phenomena. While other hypotheses, like Van might offer explanations for some isolated anomalies, perhaps doing a decent job with certain galactic rotation curves, for example, they often struggle significantly when you try to apply them simultaneously to all the other phenomena. MOND, for instance, faces major challenges in explaining in a simple way observations like the precise shape and peaks in the cosmic microwave background power spectrum. That's a huge hurdle. It also struggles with the dynamics of colliding galaxy clusters like the Bullet cluster, where we see that clear separation of mass and gas. And it has difficulty naturally explaining the patterns of gravitational lensing observed in the most massive structures in the universe, often requiring those extra fields or particles we mentioned earlier, adding complexity. Only the dark matter particle hypothesis, within the framework of standard cosmology, lambda CDM, currently provides a single, unified, coherent framework that successfully addresses such a wide range of diverse phenomena, from the smallest dwarf galaxies to the largest structures and the earliest moments of the universe. It gives consistent quantitative results across all these different categories of observations: galactic rotations, lensing, CMB, large-scale structural formation, cluster dynamics, and its basic properties. Massive, weakly interacting cold are remarkably well understood in comparison to the often more complex and less predictive alternative theories. It just works better overall. So current science, therefore, overwhelmingly supports the existence of dark matter, likely composed of one or more types of new fundamental particles that will significantly extend our current standard model of particle physics. It represents a revolution waiting to happen in particle physics. And it's a testament to the scientific process, really, that despite not yet directly detecting these particles on a lab experiment, which is a major ongoing effort, the indirect evidence from cosmology and astrophysics is so incredibly strong, so consistent across so many independent lines of inquiry, that the vast majority of physicists are convinced it must be real.
And this isn't just a static theory people accept, right? The search for dark matter is one of the most active and, frankly, exciting frontiers in science right now. People are desperately trying to find it. So what does this look like in practice? How are scientists actively trying to finally, put their hands on these elusive particles, catch one?
That's an excellent question, and it's where the rubber really meets the cosmic road. The scientific community is pursuing several ambitious, complementary avenues simultaneously. It's a global effort. One major approach involves direct detection experiments. These are incredibly sensitive detectors, often built deep underground in mines or tunnels to shield them from confusing background noise from cosmic rays and natural radioactivity. Their goal is to catch a rare wink or nudge from a hypothetical dark matter particle as it passes through the Earth and happens to interact just barely with an atom nucleus inside the detector. Experiments like LUX Zeppelin in South Dakota, Xenont in Italy, and Pandax in China are typically filled with large volumes of ultra-pure noble liquids like liquid xenon or argon. They're basically hoping to observe a tiny recoil, a minuscule flash of light or ionization signal, when a dark matter particle, often assumed to be a WIMP, weakly interacting massive particle, scatters off one of those atomic nuclei. It's like trying to detect a whisper in a hurricane. Incredibly challenging. Another complementary approach is indirect detection. This looks for the products of dark matter interactions happening out in space. If dark matter particles can annihilate with each other when they collide, perhaps if they're their own antiparticles, or if they can decay over long periods, they might produce ordinary particles that we can detect, like high-energy gamma rays, neutrinos, or even positrons and antiprotons. So telescopes like the Fermi L8 satellite looking for gamma rays, the AMSO2 experiment on the International Space Station looking for antimatter particles, and the IceCube Neutrino Observatory buried in the Antarctic ice looking for neutrinos. They are constantly scanning the cosmos, especially regions expected to be rich in dark matter, like the center of our Milky Way or those dwarf satellite galaxies we talked about, searching for an excess of these potential annihilation or decay signals above the expected background.
That's quite the cosmic fishing expedition, a multi-pronged attack. Are there other types of particles being seriously considered beyond those WIMPs you mentioned? Because we haven't found WIMPs yet, right?
Absolutely. The WIMP model, while historically favored due to some nice theoretical coincidences, the WIMP miracle, has been a leading candidate for decades. But you're right, with no definitive detection yet, despite increasingly sensitive experiments, physicists are definitely broadening their search and considering other possibilities much more seriously. Another prominent and increasingly popular candidate is the axion. Axions are predicted by theories trying to solve a different problem in the standard model, the strong CP problem related to neutron properties. They are expected to be much, much lighter than WIMPs and interact even more weakly with ordinary matter. Detecting them requires different techniques. Experiments like ADMX, Axion Dark Matter Experiment, use incredibly strong magnetic fields and resonant microwave cavities, essentially trying to coax axions into converting into detectable microwave photons. It's like tuning a very sensitive radio to listen for the dark matter signal. And beyond WIMPs and axions, there's a whole zoo of other possibilities. Sterile neutrinos, dark photons, mediators of a hypothetical dark force, particles arising from extra dimensions, primordial black holes formed in the early universe. The list is long. Particle accelerators like the Large Hadron Collider, LHC, at CERN are also contributing to the search. They're trying to produce dark matter particles directly by smashing ordinary particles, protons, together at incredibly high energies. They can't detect the dark matter particles themselves if they're produced because they're invisible and weakly interacting, but they look for signatures of missing energy and momentum in the collision debris, which would imply that some new undetectable particle must have been created and escaped the detector. So yeah, it's a multi-pronged attack on the invisible, using detectors deep underground, telescopes in space and on the ground, and the world's most powerful particle collider. It really demonstrates the incredible dedication and ingenuity of scientists trying to unravel this profound mystery. #outro.
Wow. What an incredible deep dive we've had today. We've journeyed from those earliest, mysterious gravitational tugs detected by astronomers like Robert Minchin in seemingly empty space, to Vera Rubin's groundbreaking work revealing that galaxies are spinning way too fast, held together by unseen mass, to understanding how Einstein's theory of gravity, through lensing, allows us to literally map the invisible by how it bends light. We've seen how galaxies seem to be fundamentally built upon this invisible scaffold, and how even the paradoxical absence of this invisible matter in some very strange galaxies, like DF2, and that stunning separation in the bullet cluster, provide some of the most compelling proof of its crucial role. It needs to be there, usually. And we've touched on how fundamentally physics itself, through deep theoretical requirements for symmetry and completeness, and the ongoing hunt for particles beyond the standard model, is strongly pointing towards a universe far richer in particles and forces than we currently grasp.
Exactly. And this isn't just about finding some missing piece of the cosmic inventory, like finding a lost sock. It's really about a profound potential shift in our understanding of matter itself, and maybe even reality. The core question, as we've discussed throughout this deep dive, perhaps isn't just does dark matter exist, but more fundamentally, are new particles and forces required to explain the universe around us? And the answer, coming loud and clear from both the overwhelming wealth of astronomical observations and the compelling demands of our fundamental theoretical frameworks, is a resounding yes. Something new is needed. Whether we ultimately call these required new constituents dark matter or mirror particles or axions or something else entirely that we haven't even conceived of yet, the universe is clearly built on far more than the ordinary matter we currently know and interact with directly. Discovering the true nature of this dark sector will undoubtedly revolutionize our understanding of fundamental physics, potentially connecting cosmology and particle physics in entirely new ways.
So, as you go about your day, maybe tonight, look up at the stars, or just consider the world around you, the seemingly solid reality. What else might be subtly shaping our reality, just beyond the reach of our current senses and instruments? Hiding in plain sight gravitationally? What invisible forces, what unseen particles might be at play all around us, waiting to be unveiled by the next generation of experiments or theoretical breakthroughs? The universe is clearly full of secrets, profound secrets, and dark matter is just one of them. Perhaps the biggest secret revealed so far, dominating the matter budget of the cosmos. What will be the next groundbreaking discovery that completely reshapes our cosmic view and takes us even further beyond our current understanding? It's exciting to think about. Keep that curiosity burning. We really hope this deep dive has given you a solid shortcut to being well informed about one of science's greatest, most active mysteries, and perhaps inspired you to look a little deeper into the unseen fabric of our truly amazing universe.